All right, welcome to lesson 3 on experimental probability. There are a lot of new terms that you need to be familiar with, so I just wanted to go through those first. And so one of the major branches in modern mathematics is the mathematics of chance, commonly called probability. So the probability is a number that gives a measure of how likely an event is to occur. So think of the probability that it's going to snow, or the probability of a snow day tomorrow. A lot of weather forecasts, sports, you see a lot of probability of teams winning. And so that is a major part of most of our everyday lives. The probability theory deals with chance, random variables, and the likelihood of outcomes. How likely is an event to happen? So some definitions that you should be familiar with that we'll use throughout the next couple lessons is an experiment. So an experiment is a sequence of trials in which a physical occurrence is observed. So think of a coin toss. You're tossing a coin 10 times and observe how many heads you get. This is the experiment that you are conducting. A trial is one repetition of an experiment. So one toss of the coin. If you repeat it multiple times, you have multiple trials. The outcome are the results of your experiment. So if I toss a coin, I have one trial is one toss. If I do 10 tosses, that's 10 trials. And so that's my experiment here. And you can see here, when I toss a coin, it's your options or the outcomes, possible outcomes are either heads or tails. The sample space is the set of all possible outcomes, so sometimes referred to as the universal set. So you saw the last lesson, we used the S or the U to represent the sample set. The possible outcomes are heads or tails. The event space is a collection of a group of outcomes from S, a subset of the sample space. So capital letters, excluding S, are used to represent an event set, and it contains a specific outcomes from the experiment you are interested in. So it would have either the heads or the tails in this example with the coin toss. So for example, if you are trying to find the probability of rolling an even number with a die, then the sample space would be 1, 2, 3, 4, 5, 6. You have 6 sides to your die, and the event space of A would be 2, 4, or 6, because those are the even numbers within my sample space of 1, 2, 3, 4, 5, and 6. A simple event is an event that consists of only one outcome, so the probability of rolling a 2. A compound event is an event that consists of more than one possible outcome. So you have 2 outcomes here. Example, rolling a 2 on the first roll and an even number on the second roll. There are 2 possible outcomes there. The probability of an event is a number between 0 and 1. So 0 is impossible, 1 is certain. It's for sure going to happen. It can happen. For any event A, the probability of A is the probability of event A. So the probability of event A is greater than or equal to 0, but less than 1. A fair game, a game in which all players have an equal chance of winning, so there's no bias involved. Everyone has an equal opportunity to have an outcome, or if you think of a dice or a die, you would have 6 sides. All 6 sides are present. There's nothing hindering one of the sides. If you have a coin, the coin has 2 sides, heads and tails. We don't have a coin that just has 2 heads. Otherwise, that would not be a fair game. Simulation, an experiment that models an actual event. And the law of large numbers. This is an important one, especially in stats. If you go on to do more courses in stats or even research, the more times an experiment is repeated, the closer the outcome should be to the theoretical probability. So in theory, we have a certain probability that should occur. But when you actually do the experiment, you often see a different outcome. But the more times you repeat this experiment, you should reach a probability that is closer to the theoretical probability. And we'll do theoretical probability in lesson 4. So here I just want to go through two types of experiments. So an experimental probability, if you look at this equation here, this is a good equation that you want to make note of. You should also know I posted a formula sheet with equations. It might be a good little side note to have next to you when you're working through these problems. It's under lesson unit 1. So experimental probability is the observed probability of an event. So the P, the event A occurs, is the number of times A has occurred over the number of trials. And you'll see this is a little more straightforward as soon as I get into an example here. So experiment 1. Since we're online and this is virtual, it makes it a little harder for me to actually run these experiments in front of you. But if you wanted to, you could do this at home on your own. And if you had to toss a coin and record the outcome, you would repeat this 50 times. And you're going to find and list the experimental probability of tossing a head after 10, 20, 30, 40, and 50 trials. So we have a coin. There's two sides to a coin, so a heads or a tails. So theoretically, you should be observing a probability of 1/2. Okay. So if I look at, I'm looking at tossing a heads after these trials. So if I look at outcome set 1, I've tossed the coin 10 times over, and I can see set 1 has a probability of heads. If I look at it, I have 1, 2, 3, 4. So 4 out of 10 would be the probability of tossing a heads. If I look at set 2, set 2 has a probability of 1, 2, 3, 4, 5, 6, 7. So 7 out of 10. So you can see the difference there. One is about a 40% chance, one is a 70% chance. So if you look at them individually, you are not close to the theoretical probability of 1/2 or 50%. But as you see, we have more sets that occur. And if I combine them, so if I look at these two, 4 plus 7, I have about 11 out of 20, which is about 55%, which is closer to the theoretical probability stated in the law of large numbers. If I go on to set 3, the probability of heads is 1, 2, 3, 4, 5, 6, 7, 7 out of 10. So I'm going to continue to add these up to show you the law of large numbers. And so now I have 11 plus 7, so I'm at 18 out of 30. I'm at about 60%. Set 4. Probability of landing a heads, tossing heads, 1, 2, 3, 4, 5, 6, 6 out of 10. 18 plus 6 would be 24 out of I've now run 10, 20, 30, 40 trials. And that's also around 60%. And set 5, the probability of heads is 2 out of 10. So that's now at 26 out of 50, which is 52% chance that I would toss a heads. Okay, so you can see as you combine and run more trials, you're more likely to end up, and it's more accurate and a better representation. If I just do one set, it could be just by chance that I get a 70%, which is not close to the theoretical. So in theory, the more trials you run, the more sets you run, the closer it should be to your theoretical probability. So this is a similar one here for experiment 2. Again, it's hard for me to show you this dice, or the die, which is one of them. So here I have rolling. I'm going to roll a single die, and record the outcome. So I have the process is going to be repeated 50 times. So 5 trials. Every set will have 10 rolls. And I'm going to find and list the experimental probability of rolling a 4. So I'm looking at rolling a 4 after 10, 20, 30, 40, 50 trials. And I wrote here a die has 6 sides. So theoretically, if I want to see what's the probability of rolling a 4, it should be 1/6, which is about 17%. Right? The 4 is on one side. I have 6 sides, so 1 out of 6 sides. So I roll this die 10 times over, and the probability in my first set of rolling a 4 is 0 out of 10. Yeah, I have 10 rolls here and 0 out of 10. So that's far off, I guess, in a way from my theoretical 1/6. Okay. Now if I look at my second trial, my second set is 2 out of 10. So when I combine these, I now have 2 of 4s out of 20 rolls, which is now at 10%. If I look at set 3, the probability of a 4, I'm running out of space here. The probability of a 4 is 1 out of 10. And just like above, if I add that, I now have rolled 4 3 times out of 30 trials. And again here, this now is at 10%. And if I look at the next one, let me just make sure these are correct. Yeah, 10%. Trial or set 4. So set 4, the probability, if I look through all the numbers here, I do not see a 4 that was rolled, so I have 0 out of 10. I'm still at rolling 3 4s, but now I have 40 trials. This takes me to 8%. And if I look at probability of 4 here, I have 1 out of 10, which gives me 4 out of 50. And that would give me 8%. So you can see theoretically I should have had a 17%. I do have more outcomes possible here. So my sample space is larger. I do have 6 instead of the 2 like you saw above in experiment 1. So I would probably benefit from doing more than just 5 trials to get closer to the theoretical. But sometimes the experimental is not what should happen in theory. But the closer you do it, the more trials you do, to follow the law of large numbers, the more times an experiment is repeated, the closer the outcome should be to the theoretical probability. Okay, so you'd probably want to repeat this a few more times to get closer to that 17%. So an experiment can be simulated using random numbers. The random numbers can be generated using a calculator, tables, or a computer spreadsheet. If you use Excel, you can do that in that program as well. You can use Google Sheets. If you even Google random number generator, there are many programs now online that will do that for you. When you're designing a simulation, it is important to ensure that the experiment has the correct sample space and is fair. So every number or every trial should have an equal opportunity to reach or achieve your various outcomes. And there should be nothing hindering it. Shouldn't be any biases, and everything should have a fair chance. When implementing an experiment, be sure to organize your result in a frequency table that lists all possible outcomes and the number of times each outcome occurred. So frequency tables, if you had something like, if I just listed numbers, 1, 2, 3, 4, how often did you see a 1? This is what a frequency table would be like. This would be how many times. Say I saw it 2 times, 3 times, 5 times, 6 times. Okay, so this is the term or the outcome and how many times it occurs. So that just helps you. So you can see it here. In example 2, I listed it as P4. How many times does it occur? That's a good frequency table that you can use to help organize your data to determine your results. So I know in the note it said page 206, that's an older textbook. The textbook that is posted, you're gonna go to page 8. There are 2 examples. I suggest reading through them because the more you read through them and look through different examples, the better understanding you should have of the concept. And then you're going to go to the unit outline that's posted and complete the homework assigned with lesson 3. Thank you.